Welcome to a video on solving advanced absolute value inequalities. In this video, we'll look at both the between cases and the outside cases. Let's get started. Absolute value inequalities can be rewritten as compound inequalities connected with and or. This means we'll be looking for the intersection or union of two inequalities as our solution. You may want to review compound inequalities before moving on. Absolute value inequalities fall into two categories. For any real number C and algebraic expression A, absolute value inequalities will fall into one of the following two categories. The is less than category, which includes is less than or equal to. This is when you have the absolute value of the algebraic expression A is less than C, or the absolute value of the algebraic expression A is less than or equal to C. And then there is the is greater than case, including is greater than or equal to. This is when you have the absolute value of the algebraic expression A is greater than C, or the absolute value of the algebraic expression A is greater than or equal to C. So these two categories just depend on what type of inequality is related to the absolute value. The is less than case is often referred to as the between case, and the is greater than case is often referred to as the outside case. And this has to do with how you find a solution to these two cases. Let's go into greater detail for the solution for each of these two scenarios. Let's start by taking a look at the is less than or between case. These definitions are written generic terms, but we'll look at some problems toward the end of this video. For any positive real number C and algebraic expression A, if the inequality is the absolute value of A is less than or equal to C, then the solution set is negative C is less than or equal to the algebraic expression A, which is less than or equal to C. So the algebraic expression A is between negative C and C. If the inequality is the absolute value of A is less than C, then the solution set is negative C is less than A, which is less than C. Once again, the algebraic expression A is between negative C and C. The only difference of these two solution sets is the type of inequality that the original problem started with. I usually remember the solution set to the less than problems by thinking less lands in the middle. There is a special case here that has no solution. If you get that the absolute value of the algebraic expression A is less than or equal to a negative number, or the absolute value of A is less than a negative number, there is no solution because the absolute value can never be negative. For example, let's say you were working the problem, the absolute value of the quantity 2x plus 3 is less than or equal to negative 5. The left side of this inequality is completely contained in the absolute value. That means that the left side is going to be positive no matter what value we plug in for x. So if we have something positive, it will never be less than or equal to negative 5. Therefore, this inequality has no solution. Let's take a look at the second case is greater than. These are often referred to as the outside inequalities. Once again, we'll write the definition using generic terms. So for any positive real number C and algebraic expression A, if the inequality is the absolute value of A is greater than or equal to C, then the solution set is the algebraic expression A is less than or equal to negative C, or the algebraic expression A is greater than or equal to C. This is a compound inequality connected with the phrase or. Both parts of this compound inequality are part of the solution set. If the inequality is the absolute value of A is greater than C, then the solution set is the algebraic expression A is less than negative C, or the algebraic expression A is greater than C. These are often referred to the outside inequalities because you are outside of C and negative C. I remember these by thinking it's greater to go outside. There is a special case for these types of inequalities as well. You may run into a case where the solution set is actually all real numbers. If you get that the absolute value of the algebraic expression a is greater than or equal to a negative number, or the absolute value of an algebraic expression a is greater than a negative number, this is always true because the absolute value is never negative. So in this case, the solution would be all real numbers. For example, if you were working the problem, the absolute value of the quantity 2x plus 3 is greater than negative 5. On the left side, the absolute value would be positive for any value of x, and that will always be greater than negative 5. So the solution to this inequality would be all real numbers. Before we start working example problems, let's make sure that we understand the solution set. A solution to an absolute value inequality is usually not just one number. The solution set contains every value of x that makes the inequality true, and typically this is going to include an infinite number of solutions. Keep in mind that the outside solution set typically includes two regions. Because inequalities have an infinite number of solutions, in math, we have several ways that we express the solution set. We will express the solution set using inequality notation, interval notation. Remember when you're using interval notation that we use square brackets to denote when an endpoint is included, and these typically correspond to the inequalities less than or equal to or greater than or equal to. And we use round parentheses to represent when a value is excluded. These are usually associated with the inequalities less than, greater than, and positive and negative infinity always receive round parentheses in interval notation. And then the third way is that we will usually graph our solution set on a number line. This is where we shade all values that are included. Just like interval notation, we have a way to represent when values are included or excluded. We use closed dots to represent values that are included. This typically corresponds to the inequalities less than or equal to or greater than or equal to. And we use the open dots to show that a value is excluded, which usually corresponds to less than and greater than. Let's take a look at a quick example here where the absolute value of x is greater than 4. In this problem, the absolute value is greater than our constant, so this is an outside problem. For outside problems, our solution was the two inequalities, x is less than negative 4 or x is greater than 4. This would be the solution set written in inequality notation. This same solution set written in interval notation would be negative infinity to negative 4 union 4 to infinity. And here we would have round parentheses on everything. Since positive and negative infinity always receive parentheses, 4 and negative 4 are excluded because of the strict inequality. We could graph this solution set on the number line. We would have an open dot at negative 4 to show that it is excluded from the solution set, and then we would shade to the left. We would have another open dot at 4 to show that 4 is excluded from the solution set, and shaded to the right. Now let's take a look at the steps to solving absolute value inequalities. As we do this, we'll work the example problem where we want to solve 2 times the absolute value of the quantity x minus 1 minus 3 is less than or equal to 9. The first step is to isolate the absolute value expression. Looking at this inequality, we need to isolate the absolute value of x minus 1. So I'm going to start by adding 3 to both sides of this inequality. That would leave me with 2 times the absolute value of the quantity x minus 1 is less than or equal to 12. Then I need to divide both sides by 2. That would leave me with the absolute value of x minus 1 is less than or equal to 6. So now we've isolated the absolute value part of this inequality. The second step is to check the value of C. Essentially, you want to check to see if you're in one of those special cases I mentioned. That only occurs when C is negative. So if C is less than 0 or negative, the inequality will either have no solution or all real numbers. Looking back at our inequality, we see that the value of C is 6, which is positive. This is not one of our special cases. We need to keep going. Let's take a look at step 3. Step 3 is to rewrite the absolute value inequality as a compound inequality. So you want to check to see if you're in the between cases. This is where you have the absolute value is less than or equal to, or strictly less than C. Less than lands in the middle, so you would rewrite that as the algebraic expression A is between negative C and C. If you're in the outside scenarios, this is when you'd have the absolute value of your algebraic expression is either greater than or equal to, or is strictly greater than a value C. Then you're going to rewrite as the two outside inequalities, the algebraic expression A is less than or equal to negative C, or A is greater than or equal to C. For these last two, remember it's greater to go outside. Let's look back at our inequality and determine if we are in the between case or the outside case. In this case, we have the absolute value of x minus 1 is less than or equal to 6. Less than lands in the middle, so this is telling me we're in the between case. So my solution set would be where the algebraic expression x minus 1 is going to be between negative 6 and 6. So I'm going to rewrite this as negative 6 is less than or equal to x minus 1, which is also less than or equal to 6. The fourth step is to solve the resulting compound inequality. When you're solving this type of compound inequality, you're trying to isolate the variable in the middle. So I want to get x by itself. That means I need to add 1 to the middle. But of course, what I do to the middle, I need to do to the two other pieces of this inequality. So I'm going to add 1 to the left side and add 1 to the right side. Now let's total everything up. So on the left side, we'd have negative 6 plus 1 is negative 5 is going to be less than or equal to x, which is going to be less than or equal to 6 plus 1 is 7. So this would be my solution set in inequality form. The last step is to graph the solution set on the number line and write it using interval notation. Since this compound inequality involves using the less than or equal to symbols, the solution set includes the endpoints negative 5 and 7. So on a number line, I would draw a solid dot at negative 5 because it's included, and I would draw a solid dot at 7 because it's also included in our solution set. And then the solution set includes everything between negative 5 and 7. Rewriting this using interval notation, our interval would be from negative 5 to 7 with square brackets on both negative 5 and 7 because those endpoints are included in the solution set. Let's take a look at a few more practice problems. Let's solve the inequality. The absolute value of the quantity 2x plus 1 plus 4 is greater than 11. Our first step is to isolate the absolute value. It looks like we need to subtract 4 to both sides. This would leave us with the absolute value of the quantity 2x plus 1 is greater than 7. Let's check the value of C. So C is 7, which is positive. That means this is not one of our special cases. We need to keep going. Now let's take a look at our inequality. We have the absolute value is greater than 7. Greater, we go outside. So let's rewrite this as the compound inequality 2x plus 1 is less than negative 7, or 2x plus 1 is greater than 7. Now let's solve each one of these inequalities. On the left side, we need to solve 2x plus 1 is less than -7. So let's subtract 1 to both sides. This would leave us with 2x is less than -8. Dividing both sides by 2, we would end up with x is less than -4. Now let's solve our other inequality. 2x plus 1 is greater than 7. We would subtract 1 to both sides. This would leave us with 2x is greater than 6. Dividing both sides by 2, we'd end up with x is greater than 3. So in inequality form, our solution set would be x is less than -4 or x is greater than 3. Both of these are part of our solution set. Now let's go ahead and graph our solution set on a number line. Because we have strict inequality here, the endpoints -4 and 3 are going to be excluded from the solution set. That means that we want to use open dots on the number line. So I would have an open dot at -4, and then I would shade to the left, and I would have an open dot at 3, and I want values of x that are greater than 3, so I'm going to shade to the right. Rewriting this solution set using interval notation, for the piece on the left where x is less than 4, we would rewrite that as the interval from -infinity to -4 with a round parenthesis on -4 to show that it is excluded from the solution set. And this is in union with the second interval, which would be from 3 to infinity, once again having a round parenthesis on 3 to show that 3 is excluded from the solution set. So in interval notation, I would write this as -infinity to -4 union 3 to infinity. In our next example, we'll solve the inequality 4 times the absolute value of the quantity x plus 1 plus 12 is less than 9. Let's start by isolating the absolute value. So the first thing we need to do is subtract 12 to both sides. This would leave us with 4 times the absolute value of the quantity x minus 1 is less than -3. The next step is to divide both sides by 4. This leaves us with the absolute value of the quantity x minus 1 is less than -3/4. Now if we check the value of c, c is -3/4. Since c is negative, this tells me we are in one of our special cases. So we have the absolute value on the left is less than a negative number. Well, absolute value will always be positive no matter what value we plug in for x. A positive value will never be less than a negative number. So this tells me this inequality has no solution. In our next example, we want to solve where 3 times the absolute value of the quantity 2x minus 4 is less than or equal to 5. The first thing we need to do is to isolate the absolute value. So let's add 4 to both sides of this inequality. That would leave me with 3 times the absolute value of the quantity 2x is less than or equal to 9. Dividing both sides by 3, we would end up with the absolute value of the quantity 2x is less than or equal to 3. Let's check the value of c. c is 3, which is positive. That tells me that this is not one of our special cases, so we need to keep going. Now let's check what type of inequality we have. We have an absolute value is less than or equal to 3. Less than lands in the middle. So this is a between case. So we'll rewrite this as our algebraic expression 2x is between -3 and 3. So this inequality is -3 is less than or equal to 2x, which is less than or equal to 3. Now we need to solve this compound inequality by isolating x in the middle. To do this, we'll need to divide the middle by 2. But what I do to the middle, I need to do to the other two sides. So this would simplify to -3/2 is less than or equal to x, which is also less than or equal to 3/2. So this would be my solution in inequality form. Now let's go ahead and graph this on our number line. Let's start by plotting where -3/2 and +3/2 would be. -3/2 would be halfway between -1 and -2, and +3/2 would be halfway between 1 and 2. We're going to have a solid dot on both -3/2 and +3/2. Those endpoints are included in the solution set because we have the inequality less than or equal to. And our solution set for x is everything between those two values. Our solution set would be the interval from -3/2 to 3/2 with square brackets on both -3/2 and 3/2 to show that they are included in our solution set. For our final problem, let's solve 2 times the absolute value of the quantity x minus 3 minus 8 is greater than or equal to -10. Our first step is to isolate the absolute value, so we'll need to add 8 to both sides. This leaves us with 2 times the absolute value of the quantity x minus 3 is greater than or equal to -2. Dividing both sides by 2, we would end up with the absolute value of the quantity x minus 3 is greater than or equal to -1. Now our value of c is -1. Since the value of c is negative, this tells us we're in one of our special cases. So let's look at the left-hand side. The left-hand side is our absolute value. That is always going to be positive. So we have a positive is greater than or equal to -1. That's always going to be true no matter what value we plug in for x. So our solution set here would be all real numbers. The way that you represent the solution all real numbers on a number line is to shade every number on the number line. In interval notation, this would be the interval from -infinity to infinity. And that's it for this video. Thanks for watching.